start recording. I'm happy to introduce the lecturers for the lecture today. It is about the phenomenology of inflationary preheating. The speaker today is Marcos Garcia from National Autonomous University of Mexico, UNAM, in Mexico. The first part of the lecture is the fluid picture of reheating. Actually, everyone in this Zoom might be familiar with inflation, hopefully, and try to learn more about reheating after inflation phenomenology. So we welcome the speaker, Marcos, today.
Okay, well, thank you so much for the introduction. And also thank you so much for the invitation. It's honestly a great pleasure for me to have been invited to deliver these lectures. First of all, because this is a topic that is very close to my heart. Most of my research involves reheating in one way or another. And for me, this was also a good opportunity to gather together, a series of somewhat disconnected notes or papers, and try to make of them a coherent body of series of lectures, let's say. So, as you said, the title of the lectures is the Phenomenology of Inflationary Reheating. That means that I'm going to be talking about reheating, but also about the some connected phenomenological problems in cosmology that involve reheating one way or another. So for this reason, I decided to divide the lectures in this way. So we're going to be meeting 3 times this week. And today, the title is The Fluid Picture of Reheating. What this means essentially that today what I'm going to try to address is, first of all, what is reheating, and try to put together the macroscopic, let's say, the fluid picture of reheating using mostly perturbative tools. Okay, so we're going to be tracking temperatures, energy densities, and so on. Again, just looking at the macroscopic equations of motion. The microphysics, the actual details that involve the particle interactions during reheating are going to be discussed tomorrow. So that's why the title is that one. So tomorrow, I'm going to be talking, for example, about still some perturbative reheating, but now looking more into the details of the thermalization process and the phase-space distribution of the inflaton decay products. And also I am going to cover this fantastic topic of preheating, of non-perturbative particle production after inflation. That, of course, I mean, just learning about preheating would take us many more lectures. So unfortunately, I'm going to only have to, I will only be able to tell you mostly about the basic stuff, because for lecture 3, I really want to talk about some of the promised phenomenology. And due to the fact also that there are many things to say, I'm going to focus on mostly on 2 observables. So I'm going to talk about the connection between reheating and the CMB, and the connection of, between reheating and dark matter. But along the way, I'm going to pick up some extra things. For example, if time allows, we can get all the way down to warm inflation today, which is another interesting topic that involves reheating. And I tried my best to include the relevant let's say the original or the most relevant references in each one of the slides that I present. If I am missing some, papers or citations or whatnot, then you'll have to apologize to me. Here is a collection of these, well, not all of the references, but the most important ones, I think. So in any case, as I said, this is not supposed to be a complete list of references, but this is like the Matryoshka dolls, where you go to one of these papers and then you look at the bibliography section, and then there's 100 papers in there, and you can continue diving deeper and deeper into the literature. So I think that's a nice exercise, and there's no point in showing here hundreds of different papers. So having said that, I think we can start, introducing the topic of, well, first inflation and then reheating, so that we can begin investigating its phenomenology. So these few first slides are intended to be a reminder of what we mean by the standard lambda CDM model, what we mean by inflation, and most importantly, I guess, to introduce notation, because the notation used in the literature is not unified. So I am going to use my particular, my preferred set of Greek letters for notation. But if you go to the literature, you might find things written in a slightly different way. So this first slide is, as I said, just a reminder of what the standard hot Big Bang model is. So through observation, mainly, we know that at the largest scales, the universe is, to a very good approximation, homogeneous and isotropic. It looks essentially the same no matter where you look at. And we describe it by means of the Friedmann-Robertson-Walker metric, which is written here. So the space-time interval ds is written in terms of, in this case, a set of spherical-like coordinates. This is the cosmic time coordinate. Here, A denotes the scale factor. And as I said, okay, so here's the radial coordinate, the angular coordinates, and we have here in the denominator of dr this bit that tells us whether or not the universe is positively curved, negatively curved, or spatially flat. So this k can take values +1, -1, or 0 if we normalize it, essentially. So it tells us what is the spatial geometry of space, right? Now, assuming this is the metric of space-time, as I mentioned, we can substitute it into Einstein's equations. And from there, we obtain what are known as the Friedmann equations and the continuity equations that tell us how the expansion rate of the universe, which is quantified by the Hubble parameter, it is the time, the logarithmic time derivative of the scale factor, is affected by the presence of matter and radiation in the universe. So this rho is the energy density of any species that is present. This k is the same k as here, and this lambda is the very well-known cosmological constant that drives the current accelerated expansion era of the universe. So this is Friedmann. This is the continuity equation. So rho determines what h, how h evolves. Sorry, what h is, and therefore how a evolves, and h itself tells us how rho changes. So the energy density can be diluted or not due to expansion, depending on what the pressure of the particular species is. And the relation between pressure and energy density for a perfect fluid can be can be parameterized in terms of its equation of state. So we generically write P is equal to W times rho. This W is very unoriginally called the equation of state parameter. So it has a terrible name, but that's how we call it. And as I said, depending on what kind of degrees of freedom your universe contains, it has different values. So for non-relativistic matter, the pressure is essentially 0. I mean, it's not always exactly equal to 0, but if it's perfectly cold, this W is equal to 0. And substitution in this equation tells us that the energy density of dust or matter-like fluid redshifts like -3 power of the scale factor, and the scale factor, if the universe is dominated by these matter species, grows with the 2/3 power of cosmic time. For radiation, We know very well, just even remembering the black body problems in thermodynamics, that this equation of state parameter has to be 1/3. Radiation has pressure. The energy density redshifts faster than in the case of matter. It redshifts like the -4th power, and the scale factor grows slightly more slowly. For vacuum, which would be, for example, the case of domination by lambda, the equation of state parameter is equal to -1. The energy density is a constant. It is not diluted by the expansion of the universe, and the scale factor grows exponentially fast. Okay, so these are the classical solutions for the hot Big Bang model. And in the case of ultra-relativistic particles, if we assume that these particles are in thermal equilibrium, we can even write down the relations between the temperature, the instantaneous temperature of this plasma, let's say, and the thermodynamic quantity. So energy density, pressure, and entropy. This G star is the effective number of degrees of freedom in the plasma. Here, I forgot to put some sums. So this is the total number of relativistic degrees of freedom in equilibrium in the plasma. So it's the sum of the bosonic degrees of freedom. And then there's this factor for the fermionic ones, because we normalized things to the Bose-Einstein distribution, okay? And one thing to remember is that in the absence of injection of particles into the universe, entropy is conserved, the total entropy is conserved. And so just by looking at this expression for the entropy density, we know that the temperature has to go as the inverse of the scale factor, weight by this number of degrees of freedom. Okay, so that's the reminder of this. Oh, sorry. And so, so what? So yeah, so this is the standard hot Big Bang picture is essentially that if we look back in time, the universe, given the fact that it's expanding now, should have been contracted, and at some point it must have had a very small size and a very high temperature. Okay, so this picture of a universe that is dominated by radiation at very early times, probably produced by some, well, Big Bang, that hence the name, is not without issues, as I'm assuming most of you know, right? So there's some problems about this standard picture. One of them is known as the flatness problem, and this is related with the fact that the universe that we observe today is, for all intents and purposes, spatially flat. Okay. If we look at the Friedman equation, we can check that it defines a critical density for which the spatial flatness is exactly equal to 0. So this K is equal to 0. We look back, we said K equals to 0, we can absorb lambda into rho, we can define an energy density for the vacuum energy, essentially. And so H would be simply related by rho without the K. And that defines the, critical density at any time. In terms of this critical density, we can define what is known as the density parameter. It is simply the energy density of the corresponding species that we are looking at, normalized by the critical density. And it turns out that the one that we measure today is essentially equal to 1. Okay. In particular, if we look at the Planck, the latest Planck satellite results, which are shown here as a form of a plot relating this parameter omega k, which is not exactly an energy density, it's just a way to parameterize the curvature of the universe, compared to omega m, the density contrast for matter. It turns out that the CMB measurements tells us that this omega k is, the value that they quote is 7 times 10 to the minus 4 with an uncertainty that is even higher than this value. So essentially, the Planck observations are compatible with omega k being equal to 0. And so the universe is presently spatially flat, which, is a result. Now, the problem is that this observation that omega is equal to 1 is not stable. As I mentioned before, sorry, I didn't justify it, but the early universe has to be radiation dominated because of the way the energy density of radiation redshifts compared to that of matter. And it turns out that if we assume then that at early times we only have radiation domination, so we can relate energy densities and temperatures for the whole universe, and we assume that expansion is adiabatic, one can check that this quantity omega minus 1, okay, is a growing function with a decreasing temperature. So we can relate its value at earlier times with its value at the present time by by relating the present value of the scale factor and the Hubble parameter to the earliest values of A and H. Okay, in this case, go like a square. So again, just manipulating this equation, again, remembering that at early times the universe is radiation dominated, one can very easily write down an expression that looks like this one. Okay, so omega minus 1 at early times is related to the presently measured value of omega k and the temperature at that early epoch. And if in particular we substitute this t to be a high, a sufficiently large value, let's say the God scale, which doesn't even get to the Planck scale, then if we are to measure omega k to be this number, then omega minus 1 at early times must have been as small as 10 to the minus 58. So we have to fine tune this omega to be equal to 1 by 58 orders of magnitude if we are to observe a universe that is as flat as it is today. So that's the flatness problem. It is related with the age of the universe, essentially. There's also the horizon problem, the fact that if the universe is dominated by some fluid with an equation of state parameter that is bigger than minus 1/3, the distance that light emitted from some particles, some process at let's say the beginning of the universe to the present epoch could not have covered an infinite amount of distance, because the speed of light is finite, and so we can only be causally connected with a finite sized sphere that is called the particle horizon. So in particular, well, the definition of the particle horizon is this one. So dt divided by a is just the co-moving distance that a ray of light can cover, multiplied by a gives you the physical distance. And for equation of states that go like this, it is essentially proportional to the inverse of the Hubble parameter. So what we can do is now think about our present particle horizon and relate it to the particle horizon at later times, okay? So of course, by definition, if we can see things in the CMB, that means that they lie in our particle horizon at the present time. This picture is showing the difference between what is known as the co-moving horizon and the particle horizon. The co-moving horizon is essentially just h to the minus 1. In the matter-dominated era, there is a difference of a factor of 2 between these two horizons. So that's why this circle has a radius that is half of the other one. But these particle horizons grow with time, or equivalently, they shrink if you look back in time, meaning that 2 points that are currently inside the horizon and therefore are, well, yeah, they're currently inside our horizon, would not have been in causal contact with each other at earlier times. In fact, one can connect the size of these horizon at the recombination. It turns out to span an angle as small as 2 degrees in the sky, meaning that, again, we should see a very inhomogeneous CMB radiation in the sky, because anything that is separated by more than 2 degrees would not have been in causal contact. But that, of course, is in conflict with what we see. We see a very homogeneous CMB radiation with fluctuations as small as 10 to the minus 5. Oops, sorry. Yes, so that's the horizon problem. There are some other problems that actually gave birth to inflation, because before we even knew what inflation was precisely, one of them is the problem of magnetic monopoles. These kind of relics can be produced when a grand unified group that contains the standard model gauge group is broken to the SU3 cross SU2 cross U1 group. So if there is a U1 factor in the group, there's always some topological relic in the form of magnetic monopoles. These things are heavy, they're stable, and they might overclose the universe. As a matter of fact, if one assumes that only one monopole is produced per horizon at the critical temperature, at the temperature at which the gauge symmetry is broken, then, and this is related to the fact that, you know, we have a lot of horizons at early times between our present Hubble radius, the relic abundance of these monopoles would be as big as 10 to the 18, which would lead to a very, very, very different universe from which the one we observe today. So that's the unwanted relic problems. There's also the problem of small-scale inhomogeneities. This is due to the fact that density perturbations grow linearly during radiation nomination. And in fact, between the Planck time and recombination, this would mean that perturbations would grow by a factor of 10 to the 57. And if in particular one considers a galaxy as a fluctuation, so it has the order of 10 to 79 particles inside of that galaxy, then Poisson estimate of how big the fluctuations would have been at the beginning of times would predict roughly that the size of these fluctuations relative to the background would be as small as 10 to minus 40, which is a tiny number, but then, you know, the separation in time between the Planck era and recombination would make these fluctuations to be as big as 10 to 17, which is of course not a fluctuation anymore. So, and these would be related with the temperature fluctuations in the CMB. So it is very difficult to have fluctuations at the beginning of time that are so small that they would lead to what we see in the cosmic microwave background. Let me not elaborate too much on this point. And so, as I hope most of us know now, inflation was proposed as a solution to these fine-tuning problems, let's say, okay? So inflation is this hypothesized early epoch of accelerated expansion of the universe. Generically, inflation essentially means that the expansion of the universe is accelerated, that is, the second derivative of the scale factor grows, which is equivalent to, well, which can be realized by a universe field with some species that has an equation of state parameter that is less than minus 1/3, okay? And in particular, this can be driven by some vacuum energy, such as the cosmological constant that is present today, for example. So vacuum energy has an equation of state parameter equal to -1. I will show an example in a couple of slides. And if this is the case, I already mentioned in the standard model slide that the scale factor grows exponentially with time. The time scale, the exponent, okay, is given by the Hubble parameter times t, and we define this variable n. Is known as is called the number of e-folds that tells us how many times in e the universe grows during this accelerated epoch of expansion. Okay, so this simple suggestion, let's say, can solve this set of problems and some other problems that I'm also not talking about. For example, for the flatness problem, we said that omega -1 has to be fine-tuned by many orders of magnitude. If we have an early epoch of expansion, then this denominator, h, is a constant, a grows exponentially fast, and so this omega -1 is driven to essentially 0 if we have a sufficient amount of e-folds of growth. And in fact, you know, if you compare to the number that I quoted before, 67 e-folds is enough to lead to the present value of the curvature parameter. So inflation can solve the flatness problem simply by, well, flattening the universe by making it expand very fast. The horizon problem can be solved as well because moving horizons actually shrink during inflation. So one can start with, well, here's the same picture that I showed before. If we add inflation to this, then the moving horizon would be this big, this big sphere that would contain the CMB and probably more. It would shrink during inflation, take its value that we naively extrapolate to the beginning of times and then grow again after inflation. So in other words, the particle horizon, the physical distance grows exponentially fast. And therefore, an initially small causally connected patch can easily encompass the entire observable universe. And in this case, again, something like 60 or more e-folds is enough to solve the horizon problem. For unwanted relics, one needs a little bit more of an assumption. So if the God scale is broken above the inflationary scale, that is, we produce the monopoles before inflation takes place, then just because of the fact that these monopoles redshift like matter, its density parameter would then be scaled down by a factor of e to the minus 3m. Okay, so essentially we get rid of monopoles. We can end up with just a few of them in the whole observable universe, or just one, let's say. In fact, all matter and all radiation are going to be diluted. In particular, for radiation, the temperature will go down as e to the minus n. And so the universe ends up being supercooled, okay? The vacuum energy that fills the universe after inflation has to be converted back into ordinary and dark matter and radiation. And so this leads to the graceful exit problems. After inflation, the universe has to be reheated because it ends up being essentially empty besides the vacuum energy. For the small scale in homogeneities, let me just very briefly mention this because I'm going to go back to this in lecture 3. The idea is that due to the exponential expansion, a quantum fluctuation in the field and in the metric is going to be stretched out to become a classical perturbation, and soon such a fluctuation will correspond to length scales that are larger than the horizon. They lose causal contact with themselves and therefore freeze to the horizon crossing value until they re-enter at much later times during radiation or matter domination and become density fluctuations. And so these fluctuations can remain perturbatively small with respect to the background density until later times because they don't evolve, they're frozen, unlike the case of just a radiation field universe at early times. So inflation solves these problems, which is very good. And now the task is to construct models of inflation that work, that can lead to the sufficient amount of e-folds, at least at the background level, and that also reheat. Okay, and that is the key thing that got rid of the original, let's say, well, the second original, the original version of inflation was even more complicated, and it was related with extensions of Einstein gravity. For those of you who know that, the Starobinsky model. But the original Guth paper about inflation was dealing precisely with the role of inflation as a solution to the problems of grand unified theories. So that's what's called old inflation. The idea behind old inflation is to realize the inflationary universe scenario by considering a field theory with a first order phase transition by bubble nucleation. Okay, so if we remember, I was talking about high temperatures in the early universe, and so in principle, if we have, not in principle, in general, if we have a field, a scalar field, which I'm denoting here by phi, and I'm going to be denoting by phi from now on the degree of freedom that is responsible for inflation, which is called the inflaton field, then the potential of such a field, if it is in thermal contact with a bath in thermal, if it is in contact with a bath in thermal equilibrium, will have a correction to its potential in the vacuum that is given by the, I'm hoping, well-known expression. If you don't know this expression, forget about it. The only thing that is important to keep in mind here is that finite temperatures can lead to corrections, to deformations of the potential of a scalar field that depend on the temperature of the plasma, and that also depend on the effective mass that this field acquires in the plasma. It's related with screening effects. So in the Matsubara formalism of finite temperature field theory, one can compute these corrections at, this one is the one given at one loop. It contains the quantum correction and the temperature correction. And the point is, again, that generically for a field theory at high temperatures, one needs to take this thing into account. And so what Guth in particular and other people thought, well, is okay, let's try to exploit this fact and drive inflation by sequestering this inflaton field in a false vacuum, okay? So one example that was constructed was an example in SU5 grand unified theory. So SU5 would be the grand unified gauge group that breaks down to the standard model gauge group, and that then breaks down to the SU3 cross U1 electromagnetic group after symmetry breaking, okay? So in this SU5, the matter fields live in templates, fiplets, and singlet. If you want to include right-handed neutrinos, the standard model Higgs lives in a fiplet, and the Higgs that breaks the God symmetry is an adjoint field, and its potential can be written in a formal way. Okay, what is the exact values of these parameters and this expansion is not important. The idea, the main idea, as I mentioned, is to try to sequester the inflaton field in a false vacuum. So this is a schematic way of how inflation would work in old inflation. At very high temperatures, the potential is deformed in such a way that this sigma field acquires a large thermal mass, and it is the only minimum of the potential is essentially located at the origin with a value of the potential which is different from zero. Okay, so the field can only live here, but if the temperature is decreased, then this potential would eventually be deformed back to the original version of the potential at zero temperature that is supposed to lead to symmetry breaking, and therefore the true minimum of the theory would be the standard model one. Okay, so the SU5 minimum is the false vacuum, the standard model minimum is the true vacuum, and if we're lucky enough to be able to construct this potential in such a way that there is a barrier in here, then the transition from this point to this point at zero temperature would have to be driven by quantum tunneling, okay? For inflation, if the universe is trapped in the false vacuum at high temperatures, that would mean that a non-zero potential energy could be translated to a non-vanishing cosmological constant. The universe would rapidly expand. This rapid expansion would cool down the universe very fast, and very quickly, this sigma would find itself trapped in this minimum, and it would have to tunnel through the nucleations of the bubbles of the true vacuum to this bottom. Okay, and it has to be emphasized that this tunneling has to be quantum. It's not thermal tunneling, because inflation cools down the universe very quickly. Okay. So this is the old inflation picture, and by itself it solves the problems of the standard Big Bang model, but old inflation doesn't work because reheating doesn't work. So that's the interesting bit about this thing. And let me go through this very, very quickly because I don't want to spend too much time on this. The point is that one can actually estimate, let's say, if we really end up in the symmetric phase or not by looking at the competition between expansion and the merger rates of these bubbles. Well, the nucleation and merger rates of these bubbles. There is a question there, yes? No? No. Okay, very good. So what? So one can estimate the tunneling rate of this process, okay? This tunneling rate is the probability of bubble nucleation per unit volume per unit time, and it can be parameterized in this form. This m is some scale associated with the potential, for example, the height of this barrier, and this b is the so-called bounce action. I'm not going into any of the details. The only thing I want to do is to count bubbles. Okay, so this is the rate at which they are produced. Then we can compute the coordinate volume, that is the moving volume of a bubble formed at the time t1. So that these things are just spheres essentially. So it's 4 pi divided by 3 times the moving size of this thing cubed. Okay, so that's the volume, the coordinate volume of a bubble formed at a time t1. then the probability of bubble formation per unit coordinate volume per unit of time is going to be this P multiplied by the scale factor cube. So remember, this was physical volume, this is coordinate volume, so they are related by the scale factor to the power 3. And so the total volume in bubbles per unit volume of space would be just the volume of one of these bubbles multiplied by the probability at which they are being produced, integrated over time. So one can compute the total volume in bubbles in terms of this rate P, okay? And at the same time, we can also calculate the probability that a given point in space is not contained in any sphere of a volume between V1 and V2. So we call that probability G, okay? This probability can be computed by exploiting the fact that the probability of a point not being in one particular volume interval is uncorrelated with the probability of a point being in a different particular volume interval. So you can think of writing G for a slightly larger volume, okay, so V2 plus dV2, okay? So they are uncorrelated, therefore this probability is just the product of the two probabilities, and this probability is essentially just going to be the reminder of computing the density of spheres between volumes B and B plus dV per unit volume of space, of course. So integration of this equation, this differential equation, gives the value of this G of B1 and B2, okay, in terms of the density of spheres between these volumes. If you're interested in the details, you can look at the original reference or work out this algebra. The point is that we can compute then the fraction of space that is in the symmetric phase, okay? Remember, the universe looks like this. So the bubbles contain the broken phase, and everything outside of them contain the symmetric phase, which is the old phase, okay? So the fraction of space in the old phase is going to be equal to the probability of a point not being in any of these spheres, right? So if I am not inside of a sphere, it means I am outside of it, okay? And by this computation, it is the same as computing the probability of the point not being contained in any sphere of volume between 0 and infinity, okay? Which in virtue of this computation is just e to the minus v, the total volume in spheres, which is the one thing that we computed before, and which depends on this rate p. Okay, so we know that the universe expands exponentially fast. That means we know what this scale factor is. We can substitute it in this expression and find a result. And the result is that this fraction of all space decreases exponentially fast with the number of e-folds, okay, determined by the bubble nucleation rate. And so it goes to 0, which means it seems like inflation through, all the inflation works, okay? Most of the space is contained in bubbles. So that means most of the space is in the standard model phase, okay? Now reheating, this is the interesting part. How would reheating happen in this scenario? Well, reheating would have to occur via the collision of these bubbles, okay? Remember that the universe was trapped with this value of the cosmological constant, let's say. So all of the energy density is going to be contained in the boundaries of the bubbles. They're going to have this energy. When they collide, they release radiation with a temperature that can be determined precisely by this value of this cosmological constant. So that's how reheating would proceed in all inflation, by collisions of bubbles of the first order phase transition. The problem is that sufficient inflation and the completion of the phase transition are incompatible, okay? What does that mean? We already computed the fraction of space that would live in the SU5 phase, okay? So the volume in the old phase would be that fraction multiplied by the total volume, okay? Which we know how to compute the total volume. The total volume is just the scale factor cubed. So this is e to the 3 number of e-folds, or h times t, multiplied by the rate that we calculated before. And so there is a competition between this positive exponent and this negative exponent. If we put them together, we find that the volume in the old phase is going to increase unless this quantity, the rate multiplied by the whole parameter to the -4, is bigger than this number, which, if I am not mistaken, is something like 0.7. Okay, so there is this constraint. Unless this number is bigger than this, the volume in the old phase is going to increase. The fraction decreases, but the volume in the old phase increases. On the other hand, we want a sufficient amount of inflation, and a sufficient amount of inflation requires the number of EFOs to be about 70 at least before the fraction in the old phase is too small. If we want inflation, we want to stay in the old phase a sufficient amount of time, okay? But to stay a sufficient amount of time means that this number here has to be smaller than this number here, so that, this number here has to be smaller than this number determined by the total number of EFOs, so that we stay in the old phase a sufficient amount of time. But you can see that this constraint and this constraint are completely incompatible. This is 0.7 and this is something like 10 to the -3 or so. I don't remember the exact number, but n is 70. So this number is definitely smaller than this one, but this has to be simultaneously larger and smaller than that. So at the end of the day, reheating has killed all the inflation. The universe would have to consist of clusters of uncollided bubbles if inflation, if we have at least 70 EFOs of inflation. We can have reheating, but then we wouldn't have a sufficient amount of inflation. So this old inflation is killed precisely by considerations of reheating, which I think is very, very interesting. So let's forget about all inflation. Then we now have to look at a different model of inflation, and we have to study reheating within that particular scenario. So what I'm going to be focusing from now on is the scenarios that are called new or chaotic inflation, where we essentially ignore, well, not ignore. We assume that this trapping due to thermal effects is not present, and inflation is going to be driven by the slow roll of this inflaton field in a sufficiently flat potential. So we're not going to trap the inflaton in one false vacuum. We're going to assume that this false vacuum is a dynamical, the trapping is dynamical, it's not literal, let's say. So we can have a very flat potential here, so that the time it takes the inflaton to roll from this point to the minimum is very long, and therefore the number of EFOs can be very large, despite the fact that there is no first order phase transition here. If this flat potential is generated by by loop effects, the Coleman-Weinberg picture, this is called new inflation. If we assume that this slow roll is driven simply by the large friction that the Hubble parameter, that the expansion of the universe gives to the motion of the inflaton in its potential, then it's called chaotic inflation. And in equations, this inflation looks like this, okay? So at the homogeneous level, that is remembering that the universe is going to be made homogeneous and isotropic by inflation, the equation of motion for such a field is going to be given by an equation that is essentially the same equation that describes the rolling of a particle down a hill, okay? So we have the acceleration of the field, we have the derivative of the potential that tells us the force that is pushing the particle down the hill, and we have a friction term here. So here's the velocity of the inflaton field that is determined by the magnitude of the Hubble parameter h. Okay, so as we saw before, the Friedman equation relates h with the energy density of the field. The energy density of the field in the homogeneous limit is related with the kinetic and the potential energy of the inflaton. So it's kinetic plus potential. The pressure is kinetic minus potential. You can check this by substituting into the energy momentum tensor. And so here inflation, as I mentioned, is not driven by phase transition, is driven dynamically. If the field starts all the way up here, then in this region of the potential, the field cannot be rolling very fast. And so its potential energy is essentially constant, much bigger than the kinetic energy. So the energy density is also approximately constant. The Hubble parameter is approximately constant. The scale factor grows exponentially fast. We have inflation. We have a large friction term that makes the field roll even more slowly. So we have a lot of e-folds of inflation because the potential is so flat. And we can check that there is consistency here, that the equation of state parameter is -1. So this mimics a vacuum-dominated era, and everything works as intended, okay? And there's no problems with this. We can actually check and see that the CMB actually likes this picture very much, and that's the point of lecture 3. So for now, this is all I'm going to say about inflation, and we're going to focus on what happens after this field reaches the minimum of the potential. So it rolls very slowly here, then it eventually, finds this bending region and then starts oscillating about the minimum. This oscillate, sorry, so reheating will happen while the inflaton oscillates about this. And that means we have to understand the nature.
Marcos.
Yes.
Okay, thank you. So now it's time for some questions, if any.
Okay, very good.
If there's any, before we go into the oscillations. So if you just feel free to ask students and people in the audience.
Yeah, I have a live question. So without considering some measurement, for some eternal inflation cases, we also do not have end of the phase transition.
Oh, for eternal inflation, yes, thank you. Right. So if we have eternal inflation, then let me go back to this picture. The inflaton, yes, of course, during inflation. For now, I have been ignoring the fluctuations on top of the classical evolution of the field, but as I mentioned before, these fluctuations can be stretched by expansion. And yes, as you say, given the fact that the field is rolling very slowly down this hill, some of the fluctuations can add up and push the inflaton up the hill, in a stochastic way, let's say. So if that happens, then you're essentially stuck here and the transition doesn't happen. Yeah, that is a very good point. For now, I just was sticking with the classical picture, but yes, thank you.
My point of question is that in the old inflation cases, you mentioned that it was a problem, but in this kind of eternal inflation, it is not regarded as a problem as long as we have reheating at the observable universe, right?
Well, yeah. So for eternal inflation, as far as I understand, the thing is that this jumping, forward or backward driven by fluctuations happens essentially stochastically, and so if one region of space. If in one region of space this happens forwards, and in a different region of space this happens backwards, let's say, both of these regions are going to, in any case, expand exponentially fast. So they're going to lead to two separate regions of the universe, if that's more or less understandable. So these two regions are going to be separated by a particle horizon. And so in the end, this is what leads to some of these ideas of multiverse and so on, because our universe could be composed of regions where the expansion eventually ended and we had reheating, and regions where the expansion never ended and we have eternal inflation. The point is that in the regions where expansion ended, we can have reheating, whereas in the old inflation scenario, to have reheating, we needed the bubbles to collide with each other. Whereas in this case, if we have the two different regions, there's no problem. And just as long as we live in the sphere, let's say, where reheating happened, then we're safe. Does that make sense?
I see. So in the old inflation, the bubble never collide in the cases, and the reheating does not happen.
Yeah, in the old inflation case, the problem is that you need the bubbles to collide for reheating to happen. The energy density stored in the in the boundary of the bubbles.
I see. Yeah, I see.
Yes.
Okay. Yeah. Thank you.
Okay. So may I ask a question on this point, the bubble collisions? So even if bubbles are not colliding, is it possible to reheat the universe? It's just, I mean, we have a plasma in the force vacuum,
Yes.
where I don't know, you have a coupling between bubble and the particles.
Yes.
So that when the bubble starts increasing in size, it could collide with particle.
Yes.
In the force vacuum.
Yeah. So
And
here
then it might tunnel. I don't know. Sometime, I mean, recently people are talking about some tunneling into the true vacuum, such that
Yes.
you are left with something inside. I don't know.
Yeah. No, in fact, here I'm just giving the usual how do I say, the textbook explanation of all the inflation. I was actually reading one paper not so long ago, which has a modern version of all the inflation, where you can have reheating because of I don't remember exactly what the mechanism is, but yeah, it's related, I think, with some coupling with I always forget the membrane. I don't know how to call it, the edge of the bubble, but there are modern interpretation of all the inflation. Yeah. So this is just the old case, I think, the old scenario. The issue, as always, I think, is to connect one thing is that inflation happens and you have reheating, and the other thing is that those two things give you the correct power spectrum of primordial fluctuations. That I didn't see in that paper.
I see.
So inflation happens, but I am sure if it gives to the observed tilt and tensor to scale relation.
I see.
Yes.
Okay, thank you.
But I mean, this is essentially as far as I know about old inflation.
Okay, maybe you can take some minutes.
Yeah, we can take a break. Yes.
So
can I
before we break, you have a question? Yeah.
Well, actually, I am very newbie at the inflation, so I have no clue why the page transition is related to the sudden inflation of the universe. I meant.
Yeah. So the phase. Well, the idea is the following. Let me try to rephrase what I said before. So the point is, actually, this picture is, this slide is useful. Okay. So whether or not we have slow roll or we have whatever, the energy density of the field is going to be given by an expression that looks like this one. Okay, so in the homogeneous limit, it's kinetic and potential energy. In the case when we have zero kinetic energy, we only have potential energy. And if it is, well, if we only have potential energy and it is a constant, then the Friedman equation tells us that this constant acts like a cosmological constant and therefore leads to the exponential expansion of the universe. So the point of this phase transition is that what we wanted was to have a dynamical way in which the inflaton gets trapped in a false vacuum. So in this place, with a constant potential energy and zero kinetic energy. You see more or less what I mean, right? So it gets trapped there. If it gets stopped at that point, then we can have exponential expansion and the universe inflates. Okay, so that by itself is good. I mean, that drives inflation. There's no problem with that. But the issue is that we have to go back to the standard model minimum. The presently measured cosmological constant is tiny compared to what you need in inflation. So it's, for all intents and purposes, the present cosmological constant is equal to 0 in the scales of particle physics. So we have to go from this vacuum to this one. And the issue is that if we, well, okay, at the time, people considered that in order to have a sufficient amount of inflation, it would be a good idea to separate these two minima with a barrier. because that would mean that the field would be stuck here for a long time. But if you put a barrier, then you have to transition between the two vacua to tunneling. And the tunneling implies that these bubbles are going to be formed. Why bubbles? Because as I mentioned earlier, the universe is composed by different patches that are not in causal contact with each other. So the tunneling would happen independently at different points in space that are not connected causally. Maybe that's the thing I forgot to mention. Okay, so in this point the transition happened, and then the bubble starts expanding. In this point the transition hasn't happened, but it doesn't matter because these two cannot talk to each other due to the finite speed of light, let's say, and so on. So you have a bunch of bubbles separated by distances bigger than the Hubble radius, and the problem is that here we didn't have any dynamics at all. The inflaton was just staying there. So if we are to reheat the universe, so the energy density that was contained here after the phase transition gets stored in the boundary of the bubble, let's say, and to release it in form of radiation, these boundaries have to collide with each other, like it happened here, for example. We have a big one and a small one. So this collision releases energy in the form of radiation, and this bubble is going to be filled with standard model particles, let's say, and so on. But the problem is that the universe that we see now would require many of these bubbles to collide with each other, and the problem is that means we have a competition between the amount of expansion that we need and the amount of collisions that we need as well. Okay, so they are not compatible. If we have a lot of expansion, then these bubbles get separated very fast from each other because the universe is expanding exponentially fast. If we want to keep them close to each other, then the transition happens essentially everywhere too fast before we have 60 or 70 folds of inflation. So inflation works, the problem is reheating, or if reheating works, then inflation doesn't work. But as we were discussing with Hyun-Min, there are modern versions of all the inflation that work. It's just that this was what was written at the time, you see, and the idea behind, let's say, new inflation is the fact that you don't really need this barrier to trap the inflaton. Friction is enough to trap the inflaton away from the origin for a sufficient amount of time.
Oh.
Yeah, so in that case, you were trapping this guy by a barrier. You don't need a barrier. Friction is enough. That's the whole key point of it.
Anyway, I got some feeling from your question, your answer. Thank you.
No, thank you.
Okay, thank you for your clear answer and clear explanation on the old inflation, motivation for new inflation.
Yes.
Okay, so now, so we are about time to have a break. Probably maybe we can resume our lecture in 15 minutes.
Okay.
So we can drink some coffee or drink some water. Yeah. So please come back at 11:15.
Okay, so as I was saying before, what the inflationary scenario that I'm going to be having in mind from now on is a new or chaotic inflation setup in which the inflation is driven dynamically instead of being driven by false vacuum trapping, and reheating occurs when the inflaton oscillates about its minimum. And that means we need to understand the nature of these oscillations. So, so before going into details of the oscillations, as I mentioned in one of the earlier slides, inflation is defined as the epoch of accelerated expansion. So the end of inflation occurs when the acceleration of the expansion of the universe is 0, or equivalently when the equation of state parameter becomes larger than -1/3. In this picture of the chaotic inflation, these conditions are equivalent to twice the kinetic energy being equal to the potential energy. Okay, so you can check by writing the equation of state parameter in terms of in terms of phi dot and b, that these two conditions are equivalent to this one. And I'm going to introduce a little bit of notation here. So what I'm going to be having in mind is a potential that has a minimum that can be parameterized as some monomial with power k, okay? Some examples are a potential that has a quadratic minimum. This one is, if you want a cubic minimum, you have to put an absolute value. Or you can have a quartic minimum or a sextic minimum or anything you want. So this is the parameterization that I'm going to be having in mind, okay? If you have this, then one can describe the oscillation of the inflaton about this minima in terms of two quantities, okay? So phi of t is going to look like this, let's say for a quadratic potential, and it can be decomposed approximately as what I'm calling here phi 0. It is the envelope of this oscillation. This envelope is determined essentially by the expansion of the universe. So expansion takes out, makes this amplitude of the oscillation decrease, while P of t here is a periodic function that quantifies the oscillatory behavior about the minimum, okay? So if the potential is quadratic, the oscillation is harmonic. So this P of t is nothing but a cosine or a sine function of time. But if the potential is not quadratic, then these oscillations are not harmonic, but in general, you can parameterize them as an infinite sum of harmonic functions, right? This is just the Fourier decomposition of a non-harmonic function, okay? So there's that, okay? Another thing is that for the computation of perturbative reheating, it is going to be important to notice that the time scale for the redshift is typically much longer than the time scale for oscillations. And so one can in principle, in general, compute oscillation average quantities. In this case, I am showing the result of computing the oscillation average of the kinetic energy, which by virtue of the equation of motion of the inflaton can be related with the derivative of the potential, okay? So this is something that you can check explicitly. And upon doing this, one can actually write down the energy density and the pressure density of the oscillating inflaton in terms only of the potential, okay? So we can substitute get rid of the kinetic energy and write everything in terms of the potential, in fact, in terms only of the envelope function phi 0. So for example, substituting this expression for rho phi gives us that rho phi is proportional to the oscillation average of the potential energy multiplied by this factor k plus 2 divided by 2. So if the potential is quadratic, this number is 2, sorry. But one can also check that this is in turn the same as evaluating the potential at the envelope, okay? So this phi is the instantaneous phi, the phi that oscillates, and this is the expectation value of oscillations. Whereas this quantity here is just the potential substituted at the envelope, and you can actually go back and check by plotting, let's say, which is what I'm doing here. So the potential is quadratic. If I take the square root of this rho, I should be able to recover the envelope, and that's exactly what happens here, okay? Modulo some prefactors. And the same happens if the potential is cubic or quartic, okay? So we can relate the potential at the envelope with the energy density. Same thing happens with the pressure density, and in fact, that allows you to compute the equation of state parameter of these oscillations. So it's k minus 2 divided by k plus 2, where k is this exponent, and this recovers what I'm assuming some of you already knew, that in the case of the harmonic oscillation of the inflaton about its minimum, the expansion mimics a matter-dominated era. This K2 minus 2 is 0, so if W is equal to 0, you get matter domination, although the matter is not matter, it's the oscillation of the inflaton. Whereas if we substitute K equals to 4 here, we get 1/3, and therefore a quartic potential mimics a radiation-dominated era, okay? And you can have anything in between. The other thing is that if we know what the equation of state parameter is, we can solve for the redshift of the energy density as a function of the scale factor or cosmic time. In this case, I am assuming the inflaton exists on its own. It is not coupled to anything, so the universe is only filled with the oscillating inflaton. The solution is given by this expression, so it depends on the energy density at the end of inflation, redshifted by some amount that depends on the value of K. So this exponent, this 3 in the quadratic case, it's 4 in the quartic case, and the scale factor also depends on cosmic time, depending on the shape of the potential. Okay, but of course, I mean, we want to reheat the universe. We don't live in a universe filled with an oscillating inflaton. These oscillations of the inflaton had to eventually give birth to the standard model degrees of freedom. And that leads us finally to the perturbative decay of the inflaton field. So here I'm going to I'm going to study reheating in steps, okay? The first step that I'm going to take is to assume that we can follow a phenomenological approach, okay? I'm not going to justify these equations. The justification is going to come a little bit later in the context of what I call condensate effects. But for now, we can try to guess, you know, how the energy density of phi is translated. It's transferred to a thermal radiation bath. Okay, this phenomenological approach is based on the following: if we have if the energy density of phi is decaying, then this has to be translated into a dissipation effect in the equation of motion of phi. We are losing quanta, we are losing energy density in inflatons because we are producing other standard model particles, and therefore this has to show up in the equation of motion as some friction. So what we do is we stick an extra term in the equation of motion, which we call gamma phi, just because, I mean, that's, again, this is purely phenomenological, justification comes later. So we stick an extra friction term in this equation of motion, and if we manipulate it, as I showed above, this equation of motion can be equivalently written as the continuity equation for rho phi with an extra term on the right-hand side, okay? Which is exactly doing what we were expected to do. If we ignore expansion for a minute, so take h equal to 0, this term would tell us that the rate at which the energy density of the inflaton decays with time is proportional to the energy density of the inflaton itself times a negative quantity that would be associated, therefore, with the decay rate of phi. So this is nothing but radioactive decay, except that we have an extra term here that is also telling us that rho phi also decreases because of the expansion of the universe. Okay, and notice that this phenomenological term here and this one are not are related by the equation of state parameters. So this number here and this number here are not necessarily the same. So this is good. This is telling us how an extra friction term gets rid of the energy density of the inflaton. And then we would want that energy density to be transferred to a hot thermal plasma of standard model particles. So here, for the perturbative decay of phi, we're going to model reheating as the exchange of energy between two ideal fluids. So we write down our energy momentum tensor as the sum of the energy momentum tensor of phi and the energy momentum tensor of some radiation, which I'm denoting by R. For phi, we know what the form is already. I showed it before. It's a diagonal with energy density rho and pressure related through the equation of state parameter. Whereas for radiation, we know that the equation of state parameter has to be 1/3. Okay. So if we have these two fluids and we impose conservation of energy momentum, then the continuity equation for the radiation has to have this piece on the right-hand side so that these two cancel essentially. So whatever the inflaton loses, radiation gains. And that's how reheating proceeds. And this is very simple because now we have a set of two ordinary differential equations. Well, there's another one that I forgot to write down. The Hubble parameter is determined by these two energy densities simultaneously, by the sum of them through the Friedman equation. So with the Friedman equation and these two equations, you can very easily solve for the dynamics of reheating if we assume that this picture is okay. The only need to know is how to compute this gamma phi, okay? And well, you know, if we think that things have to work out in a reasonable way, we can say, okay, you know, if we're thinking that the inflaton is decaying into radiation, then we have to look at the decay of individual inflaton quanta in the vacuum to whatever particles are coupled to phi. So here's an example where I'm assuming the inflaton is coupled to a fermion, okay, through a Yukawa coupling term in the Lagrangian with strength equal to y. So here's the relevant Feynman diagram. Phi decays into a pair of particles with coupling y. And if we assume that these two particles are very light, which would be the case, for example, if any of these two lives in the standard model. So remember, the masses of the standard model particles go all the way up to a few GeV, whereas the mass of the inflaton, I didn't show it yet, but it would be of the order of 10 to the 13 GeV, means that these masses are essentially negligible. You can compute, you know, the decay rate using your elementary tools of field theory, and the corresponding decay rate is given by this expression, okay? So it is the square amplitude that depends, of course, on the Yukawa coupling. 8 pi comes from the phase space factors, and m phi is just the mass of the inflaton. Very easy to compute. And then if we have this, that means this gamma phi is a pure number. It is a constant. And in the case of quadratic potentials for k equals to 2, you can actually write down a formal version of the solution of the continuity plus Friedman system of equations that looks like this, okay? So the energy density of the inflaton is still redshifting like matter, but now there is this extra exponential decay term precisely because this phi is decaying in the same way as, you know, radioactive decay would proceed. On the other hand, rho r is going to be sourced by the amount of quanta that you lose from phi, and its solution is a little bit more complicated. It redshifts like radiation, but it's also being sourced by this decay. So the sign in this exponential is, sorry, not the sign, the argument of this exponential is related to this one, okay? But you have to integrate over time. So these are the formal, this is the formal form of the solution. It's a lot easier, as always, to just, you know, show a plot of the numerical solution. So here's a plot. Vertical axis are energy densities. Horizontal axis are cosmic time in units of the decay rate of phi. So if gamma t is equal to 1, we should have more or less the complete decay of the inflaton, and that's essentially what happens. So at the beginning of reheating, we have an energy density equal to the energy density at the end of inflation, which I denote by rho end, okay? The energy density, sorry, this is the energy density in the inflaton. The energy density in radiation, I'm showing it as this dashed orange curve. At the end of inflation, it is essentially equal to 0. The universe is empty and cold. So when reheating is turned on, this energy density has to grow because, again, it started at 0. So it has to grow to some value. Within the first oscillation of the inflaton field, this energy density very quickly grows to a maximum value, which I'm denoting here by rho max. And after that, both energy densities are going to decrease due to the expansion of the universe, although that for radiation does it at a slower rate because it's eating up the energy of the inflaton field. So they follow this relation. I'm going to show explicitly in a couple of slides what this is. And eventually they cross at the end of reheating. So this is called rho reheating. The end of reheating is identified with the moment when rho phi and rho r are the same. And after this time, the exponential decay of rho phi is evident and the universe enters radiation nomination. Therefore, we have reheated the universe, we have gotten rid of the energy density of the inflaton and converted it to the energy density of ultra-relativistic particles that will form a thermal bath, all right? As I mentioned, there is a maximum energy density here for the radiation. Here is shown in terms of the scale factor in a linear scale, okay? And one can actually write down this solution explicitly at very early times, well before the end of reheating, in terms of the scale factor, and compute the value of this maximum energy density, okay? So it depends on the decay rate of the inflaton and the energy density of the inflaton at the end of inflation. Okay, so it depends on the initial conditions. If we further assume that the radiation fluid is in thermal equilibrium, this rho max defines what is called as the maximum temperature of the universe. It will be the maximum temperature of the universe because any other temperature has to be lower than that. Even the reheating temperature is lower. Okay, so this one depends on the initial conditions. Now, as I said, I was going to show the same picture in a different way. So now, instead of showing it as a function of cosmic time, I am showing it as a function of a scale factor, because that lets us see how these two quantities redshift during reheating. So the energy density in the inflaton redshifts like matter for most of the time until it enters the exponential decay regime, whereas that for reheating decays as at half of the rate. So that's why they can intersect. They're not parallel lines. At the end of reheating, one can compute this energy density, which is going to be just determined by making this one equal to this one, and the corresponding reheating temperature. For the quadratic case, it is given by this expression, and the important point is that it depends only on the decay rate and the number of degrees of freedom now. The maximum temperature depended on the initial condition. The reheating temperature does not depend on the initial condition. It only depends on the rate at which the inflaton decays. So what happens during inflation, reheating doesn't care. If you end up with a hot thermal plasma with this temperature as initial condition for radiation nomination, which I think is very interesting. Okay, so this is for k equals to 2 for a quadratic potential. If the potential is not quadratic, then we start seeing how this naive picture stops making too much sense, and we have to do something a little bit more clever to determine how reheating works. It is related with the form of this decay rate, at least for this diagram. Okay, if we now have a potential that is not quadratic, think for a minute of a quartic potential, then we cannot compute anymore the decay rate as if it was the decay rate in the vacuum. The reason for that is the following. If we think that, if we evaluate this rate in the vacuum, we're going to end up with a rate that is equal to 0. Why? Because the mass of the field would be essentially given by the second derivative of this potential. So that would be the mass squared, sorry. If we evaluate it at the minimum in the vacuum, phi is equal to 0, the mass of the inflaton is equal to 0, and therefore it cannot decay into anything, no matter how light it is. Okay, so that would mean that for non-quadratic potentials, reheating would not be possible, okay? But that cannot be true, of course, and that is not true. So what actually happens is that we have to think of this as not being, reheating not being the decay of inflaton quanta in the vacuum to standard model degrees of freedom. What is happening is that we have an oscillating condensate that has a lot of energy density on it. And this condensate is going to be, is being dissipated. It's not exactly decaying, it's being dissipated. It's producing particles as it oscillates. In the perturbative picture, this can be modeled in the following way, okay? What we can do is to compute the mass of the inflaton at a given moment in time by taking the second derivative of the inflaton, but evaluating it at the envelope of the oscillation. If you remember, we can relate the energy density of the field with the potential evaluated at the envelope. Here's the envelope. So we do the same thing with the mass. Okay, so the mass is a function of time. It decreases with time if the potential is not quadratic, and it depends on phi 0. Okay, so if k is equal to 2, this exponent is 0, m is a constant, and we recover the previous scenario. But if k is bigger than 2, this is not a constant, and m of phi decreases with time. Now, the fact that the amplitude of these oscillations can be very large. In fact, in practice, this phi 0 initially is as big as, well, is of order of m Planck, okay, for most inflationary models. Well, for many, not most. For many inflationary models, this phi 0 it can be as big as m Planck. So this mass can be very, very large at the beginning of reheating and then decreases in value. So the decay is now can now proceed kinematically, but this gamma is no longer a constant. It is a function of time. And that means the solution that I showed before for the quadratic case is no longer valid, okay? The decay of rho phi in particular is no longer exponential. So this is the solution approximate at early times, well before the end of reheating, where this effect of gamma can be neglected for the redshift of rho phi. This is the same solution that I was showing before in the inflaton oscillation slide. For rho r, here it depends on the coupling, so here's y, and it has this funny shape, okay? So, I mean, let me not go through this equation in detail. The only point that I'm trying to make is that you can actually compute it. And this is, I think, a good way to visualize the difference between the quadratic and the quartic case, for example. So here I'm plotting the energy density normalized to the total energy density in the universe. So here's phi at the beginning of reheating. All of the energy density is in the inflaton. None of the energy density is in radiation. For k equals to 2, if you remember, most of it stays with the inflaton until the exponential decay becomes apparent, and then the energy density is transferred from the inflaton to the radiation. So the continuous curve is k equals to 2. But for k equals to 4, given the fact that this mass is not a constant, the decay is not exponential anymore. It actually decays as a power law in time. So it is more gentle, okay? The transfer from phi to r occurs essentially throughout the duration of inflation. And the fact that it is more gentle implies that reheating happens later in time. So here's one example showing for a particular decay, for a particular coupling equal to 10 to the minus 5, the difference in the evolution of the effective temperature in the plasma when you have a different shape of the potential, okay? So as before, at the beginning of reheating, there is no radiation. It grows very fast to a maximum value. So this is T max. And then it decreases depending on how fast the inflaton is injecting entropy to the system and how fast the universe is expanding. For k equals to 2, we know already that this slope, sorry, this line goes like 8 to the minus 3/8. You just have to substitute k equals to 2. Here's the end of reheating, and now after that it just redshifts like radiation, like 8 to the minus 4. But for k equals to 4, for example, as I was saying here, the growth in the radiation is actually much slower. So the end of reheating happens for the same coupling much later, okay? So you have to wait, what, about 3 orders of magnitude more in the scale factor in the expansion of the universe to end the reheating in a quartic potential than in a quadratic potential for the same coupling, or equivalently for k equals to 2, the reheating temperature here is of order of 10 to the 10 GeV, whereas for k equals to 4 is of the order of 10 to the 4-ish, 5-ish GeV, many orders of magnitude smaller with the same coupling just because the shape of the potential is different. And you can see Tmax doesn't care about that. Tmax is essentially the same for any value of K. And here are the expressions, okay? Just in case you're interested, I'm putting them here in the slides. So very good. So you can compute Tmax. Yes, again, it depends on the initial condition. T reheating does not care about the initial condition. It only cares about the coupling, but it also cares a lot about the shape of the potential, and that's why it goes down. Okay, very good. Now, here's an interesting bit, okay? For a non-quadratic potential, we found that the decay rate ceases to be a constant because the mass of the inflaton is now a function of time. But that also means that the way the inflaton decays is going to depend on the form of the final state. If instead of decaying to a pair of fermions, the inflaton now decays to a pair of scalar fields, okay, so we can imagine phi being coupled to a scalar field via the trilinear term, where this mu is a dimension-full quantity, so it has an energy unit of 1, then the decay rate that you compute is going to have this form, okay? So it's mu squared coming from the amplitude squared divided by 8 pi, but now just dimensionally, the mass of the inflaton has to go in the denominator. But that means that if we have K different from 2, again, this decay rate is no longer a constant, it is a function of time, but now instead of decreasing, it's growing. So the decay of the inflaton for a quartic potential to a pair of scalars is actually becoming more and more and more and more efficient as time goes on. And so this plot here is very different from the plot that I showed earlier for fermions. Let me go back to it. You see for a fermion, K equals to 2 decays more sharply than K equals to 4, whereas for bosons, K equals to 4 decays more sharply than K equals to 2. And here I have to apologize because I completely forgot about this. I was meaning to do this computation and I forgot. I actually don't know what is the result for K equals to 4 here. So I wanted to compute and I forgot. So maybe next time I can come back to this. But numerically, yeah, numerically you can it works out. So yeah, eventually I'm going to fill this blank. Okay. So, I mean, you can think of a plethora of scenarios. You can think of the inflaton being coupled to gauge bosons, to anything you want. For the purposes of the lectures, I am not going to do anything too complicated. I am just going to stick with the coupling of the inflaton to fermions and to scalar and to spin zero particles to scalars, so that things are under control, let's say. And I'm going to be thinking mostly in terms of these three different vertices, okay? So the usual Yukawa decay into fermions, the trilinear decay into scalars, or you can also have the scattering, let's say, diagram where two inflatons conspire to produce two scalar fields, okay? The decay rates in the vacuum can be computed very easily. So this is just the application of the Feynman rules. For this particular diagram, you can see that the decay rate depends on rho phi. So even for K equals to 2, this decay rate is a function of time, unlike the other two, okay? And if you think of, you know, a generic potential that goes like phi to the K, you can repeat the same exercise that I was discussing before, simply by writing what is the time dependence of the decay rate. You can parameterize it in terms of the energy density of phi to some power, okay? And find what is the evolution of the temperature during reheating, for example. You can also determine the evolution of the energy densities. You can find what the duration of reheating is, etc. All of that is connected to the effective temperature in any case. And you can build this nice table, okay? So here are the three decay channels. This is the generic result, and these are three particular cases. So for K equals to 2, these two diagrams have to give the same evolution, and they do. This other diagram you see leads to a temperature that redshifts as free radiation. It just redshifts like 1/A, okay? And this means that the energy density in the radiation redshifts like 8⁻⁴, which is faster than the rate at which phi is redshifting. This means that for k equals to 2, this diagram cannot lead to the complete depletion of the energy density of the inflaton. Okay, if you want to decay, you have to do it through these two diagrams. This one cannot allow you to get rid of all of the energy density of phi because of this reason. But if you increase the value of k, if your potential is not quadratic, but it's quartic, you can see that now reheating can happen thanks to this diagram. In fact, for the decay into fermions and the scattering diagram, the temperature evolution is the same for k equals to 4, and so on. Also for fermions, you can see that this power decreases as we increase the power of the potential, whereas for this diagram, this power, increases, and this power decreases. So here in this row, reheating is more efficient, the smaller k is. In this row, reheating is more efficient, the bigger k is. Okay, and the same goes for the other one. So this is very interesting. I think you can do all these sort of things. There's another problem though, and I'm hoping to have enough time to cover these. Maybe warm inflation, we can push it to the next lecture. There is another issue here, okay? If you remember, I mentioned that for non-quadratic potentials, the mass of the inflaton is a function of time. That is also true for the decay products. You see, if I write this coupling, and if I think of phi as having a time-dependent vacuum expectation value, then this is nothing but the same coupling as the Higgs coupling, okay? So we can write down an effective mass for the fermion like this, okay? It's going to be given by the Yukawa square and the phi square, okay, for the fermion. In this case, well, you can also write an effective mass. It's going to be linearly related to phi. Well, the square of the effective mass is going to be linearly related with phi. And for this four-legged vertex, the mass is going to be linearly related, quadratically related with the BEV of phi, okay? But this phi, as I mentioned a couple of slides ago, can be very big at the beginning of reheating. It can be as big as M blank. And so unless these couplings here are sufficiently small, you can have, you might have to take into account kinematic effects. The mass of the inflaton is decreasing. This effective mass is also decreasing, but you have to see, if there is some regime where this mass can be bigger than the mass of the inflaton because of the coupling, okay? This is a time-dependent Higgs mechanism, if you wish, okay? And unfortunately, that means we have to look at the way these particles are produced now in a proper way, okay? Forget about the phenomenological introduction of the decay rate that I mentioned before. If we want to compute the correct decay rate, we have to solve the Boltzmann equation. There is no way around that. So here's just a reminder of what the Boltzmann equation stands for. Okay, perturbative particle production is always going to be controlled by the Boltzmann equation in the expanding universe. So here I am writing down this f of chi is the phase space distribution of of some degree of freedom in the universe, let's say, in particular of this particle chi, which participates in one or many processes. In this case, I'm writing one process, for example. So chi plus A plus B goes to I plus J plus whatever, both ways. The left-hand side of the Boltzmann equation tells us how this phase space distribution changes in time and due to the expansion of the universe. Because the universe is homogeneous and isotropic, this f of chi does not depend on the spatial coordinates nor in the angular variables for the momentum. And on the right-hand side, we have the so-called collision term that tells us how this f is sourced or depleted due to these interactions. So it is written in terms of the Lorentz invariant phase space factors, the usual energy momentum conserved Dirac delta functions, and the amplitudes for the forward and the backward process weight by the phase space distribution of the particles that participate in the interaction. Okay, this 1 plus or minus something is dependent on whether or not these particles are bosons or fermions. So plus for bosons, minus for fermions. Okay, Integrating the phase space distribution gives us the number density, the macroscopic number density of the field, or the macroscopic energy density of the field if we weight this integral by the energy of the corresponding momentum mode. Okay. So if we want to know how the inflaton is depleted due to its decay, we have to introduce here the corresponding phase space distribution of the inflaton and the decay products and the amplitude at which the process proceeds. Okay. So I mentioned earlier that what is decaying here is not free inflaton quanta, at least not in the fluid picture. What is decaying here is the oscillating inflaton condensate. And so its phase space distribution has to be that of a classical oscillating field. Okay. So phi is nothing but a spatially homogeneous field. Its phase space distribution, therefore, cannot depend, well, it has to be that of momentum 0. So it's a Dirac delta function in momentum. And it is multiplied, of course, with whatever we need so that integrating here, we recover the number density of the inflaton. Okay, so it has a very simple phase space distribution. It's just a delta in momentum. Okay, the decay is going to occur mode by mode. Okay, so we have to remember that these oscillations are made up of a sum of harmonic motion, let's say in time, all right? And the third assumption is that we're going to ignore the inverse decay into the condensate. What does this mean? The inflaton is going to produce particles, and these particles can also interact and reconvert into inflatons. But most of the time, these inflatons are just going to be free inflatons. It is going to be very rare that the two particles collide with exactly the required momentum so that the produced inflaton has momentum equal to 0 and can be fed back into the condensate. So this inverse decay is assumed to be negligible. And the transition amplitude that we need to put in here is going to be computed over one oscillation. Okay, as I said before, the time scale for oscillation is typically much shorter than the time scale for the decay. So that's what we do. And we need to compute a couple of things. Okay, so let's take any potential, phi to the k. If the potential is phi to the k, we can write down the equation of motion for this periodic function p. It looks like this, okay, over one oscillation. The details, you can fill them in. It's very easy, or you can look at the reference, which I don't know why I didn't write here, but it's, you know, written in the list of references in the Indico page, I think. Integrating this equation of motion, you can find what the frequency of the oscillation is. Okay, it's in general going to be a function of time, so proportional to the mass. If k is equal to 2, this whole prefactor collapses to 1. Okay, if k is different from 2, then this is just an order 1 thing. Okay, so frequency is the mass times some order 1 factor. And then you can compute the transition amplitude that I mentioned before. Okay. So the transition amplitude is that from the classical condensate, so this is the state of the condensate, to a pair of particles, okay? So it's like a vacuum transition from nothing to something. This is not the particle state of the inflaton. This is the condensate state of the inflaton. So what do? We put in here the coupling. In this case, I'm assuming phi decays into a pair of fermions. So if I substitute the coupling, I get the Yukawa coupling, the inflaton operator times the condensate ket is just the classical inflaton as a function of time multiplied by the vacuum state. And this state of two particles can be written in terms of the annihilation operators of the psi, right? More normalized to some value. Okay, so this is just the QFT1 computation. You can calculate this expectation value very easily. Since we're dealing with fermions, you end up with the spinors, U and B, sum over all spins. We get the Dirac delta function in momenta. The inflaton has momentum 0, so we only have P1 and P2. And here's when this thing is valuable, because you see we substituted phi of t as the infinite sum over phi 0 times the harmonics. And these harmonics are going to play the role of quasi-particles that allow for this decay to happen, okay? This n omega is going to be the energy of the inflaton quasi-particle, okay? With momentum equal to 0, so we can write it formally as the momentum Pn. So Pn is the inflaton quasi-particle of the nth harmonic, okay? And this whole thing defines the transition amplitude for the n harmonic of the decay, okay? So this can be computed very easily. You can compute it for the Yukawa coupling. It gives this. So this Pn is the Fourier coefficient of the decomposition of the oscillation of the inflaton field. If we have a quadratic potential, then this Pn is just one. There's only one Pn, the first one. If it's non-quadratic, then you have all of them. For a coupling of phi to a pair of scalars with any power, in particular the trilinear or the four-leg vertices, you can compute the decay amplitude. It is very easy. You know, it's just the phi 0 to the same power and the nth harmonic of p to the alpha times the coupling. Okay. We have the amplitudes. We can integrate, we can substitute them into the Boltzmann equation and integrate the Boltzmann equation with respect to the inflaton momentum. Okay, so we have an equation of motion for n of phi. So n phi dot plus 3hn of phi is equal to this whole thing in the right-hand side. Okay, so it depends on the phase space distribution of the inflaton, on these transition amplitudes, and then you have to integrate this thing to get the right-hand side. Equivalently, given the fact that rho phi is equal to n times the mass of phi, we can write down this equation of motion for rho of phi, which, if you pay attention, it's the same as the continuity equation with the right-hand side that we obtained phenomenologically, but we know now how to compute gamma phi in any case under the perturbative approximation. And this general formula is given by this expression in this square, okay? So what do you have to do? You have to add all of the, you have to sum over all of the harmonic transitions from the oscillating condensate to the final state particles, weight by the energy of the corresponding oscillating mode and the kinematic phase space factor, okay? So remember that the masses of the particles are important, and this E of n is just the energy of the corresponding mode. So if you give me the 5 minutes, I can just show you some results of the relevance of this kinematic blocking, okay? In the case of the decay to a pair of fermions, this beta of n, the beta that I defined here, and you have to average over oscillations, of course, that I forgot to mention that. So this beta of n here, this kinematic phase space factor for the decay of two identical fermions, well, this is going to go to 0. You only get this first bit, which is this one, but I'm writing it in terms of this quantity R, okay? This P here that's showing up, it's coming because the mass of the fermion is proportional to the inflaton oscillation, so that's why P is here. And this quantity R is going to be the ratio of the mass of the, well, 2 times the mass of the fermion divided by the frequency of the oscillation. Okay, again, that's essentially this ratio here, evaluated at the envelope for simplicity. So this R doesn't oscillate, the oscillation is contained in this P. And these are, it turns out to be proportional to this quantity, okay? So it's the ratio of the Yukawa coupling divided by the parameter that appears in the potential of the inflaton field, okay? Weight by the amplitude of the oscillation of the inflaton during reheating, all right? In pictures, it looks like this, okay? So this is beta cubed in this case because fermions give this power to the 3/2. This is m phi of t. It is the natural time variable for the oscillation of the inflaton. If this quantity R is very small, that is, kinematic effects are not very important, then this beta is essentially equal to 1, and you can ignore the kinematic blocking. But if R is bigger than 1, in this case, for example, R equals to 2, one naively would think that if the mass of the decay products is bigger than the mass of the inflaton, then the process should not happen, and we should not have any decay, any rate, and no reheating. But in fact, what we see is that because the mass of the fermion depends on the instantaneous value of the oscillating inflaton, at some point during the oscillation, the inflaton crosses zero, and the mass of the fermion becomes equal to zero. So here, the mass of the inflaton is smaller than the mass of the fermion, but then as the inflaton is crossing zero, it becomes negligible compared to the mass of the inflaton. Then you get kinematic blocking again, then you don't get kinematic blocking, and so on, okay? So it doesn't matter, you can always have the decay, but it is going to be suppressed because here you're losing some particle production during the oscillation. At the end of the day, the corresponding decay rate can be computed explicitly. You can write it formally in the same form as the vacuum decay multiplied by a function that depends on K and on this kinematic factor, which is going to be very important for the next lecture as well. If the kinematic factor is less than 1 or much less than 1, then this function is equal to 1 and you can ignore it and use the table that I showed before without any issues. But if it is bigger than 1, then you have kinematic suppression. But this suppression is power-like, and so you can still decay, you just decay more slowly than you would naively guess. Same thing happens for the scalars. So for scalar fields, for the 4-leg vertex, the form of beta is slightly different. In this case, it's a little bit more, it looks more like an egg, I guess, okay? But the result is exactly the same one. You can define this parameter R that tells you how much kinematic suppression you have. Let me just emphasize this bit, and I'm probably going to stop talking in the next slide. The ratio of the mass of chi of the scalar to the mass of the inflaton is proportional to sigma divided by lambda. So sigma is the coupling of the 4-legged vertex, and lambda is the parameter that appears in the potential of the inflaton. This sigma over lambda is going to be very important for the next lecture, okay? And you get the same thing. If R is small, don't worry about condensate effects. You can compute your decay rate as you would do in the vacuum. If this R is big, then you have to do the whole computation numerically, in fact, and you get a suppression. Okay, so in pictures, it looks like this. Let me stop here. Here I'm showing the decay of the inflaton, assuming we have 2 decay channels, phi to BB and phi to FF, with y equals to sigma equals to 10 to minus 7, okay? So this coupling is sufficiently big so that at early times, the decay, quote unquote, is dominated by the scattering process, okay? If you ignore the kinematic and condensate effects, you would get this dotted blue line, okay? So you will get a big Tmax. But it turns out that for this coupling, there is kinematic blocking. You see R is bigger than 1 to the left of this thing. And the maximum temperature of the universe that you see is actually smaller than the one that you would naively expect. After some time, the decay to fermions becomes more efficient than this scattering process, and this decay is the one that reheats the universe. If you decrease the coupling, Tmax decreases, but you can still have the kinematic effect. And very briefly, as I said, for k equals to 4, the opposite happens if you have the decay to bosons, phi to a pair of bosons. In this case, I'm showing the decay to a pair of fermions and to a pair of bosons. The decay to fermions is very efficient at the beginning, but the decay to bosons is more efficient at later times, and it actually grows inefficiently if you take into account kinematic effects. If R is bigger, the decay to a pair of bosons becomes more efficient instead of being kinematically suppressed. Okay, so that's something that is a bit surprising. So this, we can stop here. I think warm inflation is too much.
Okay, thank you for your nice lecture. Okay, clear discussion. So are there any questions?
May I ask about the effective mass for extra fermion and scalar?
Yes. So the effective mass for the particles. Let me go.
Yes.
Yes. Let me go back to that slide. This slide. Okay.
Okay.
Yeah. So the effective mass is essentially just it's the same story as having the Higgs mechanism in the standard model. So for a minute, you can assume you have, instead of talking about phi, you think phi as being the Higgs, okay? If you have a Yukawa coupling, that means that if this phi has a vacuum expectation value, this y times phi becomes some kind of an effective constant, let's say. And if you have, of course, a form that looks like psi bar psi, then a constant that multiplies that is a mass term for the fermion, right? So the effective mass squared for it would be the square of y times phi. In the case of the oscillating inflaton, the vacuum expectation value of phi is not fixed. It is evolving with time. And that's why you have to do all these checking of the kinematic blocking effect, because this mass of the fermion is an oscillating function in time. So at some moment of the oscillation, you can have kinematically blocked decay, while at another time of the oscillation, the phase space can open up because the inflaton crosses zero, and therefore the mass of the field becomes equal to zero. So you can produce particles for a little bit of time, and then the process shuts off again, and so on. For the scalars, the story is the same. Let me focus on this one because it's easier. If you have a vacuum expectation value of phi, this whole thing 1/2 times m squared, chi squared is a mass term for the scalar. So the mass square is just sigma times phi squared. And again, the interesting bit here is that the inflaton is not fixed. Sorry, the BEV of the inflaton is not fixed. It is evolving with time. In the perturbative picture, this is the funny thing. In the perturbative picture, this oscillating mass implies that at some point in time, you can have kinematic suppression, okay? The same idea. You produce less particles because the mass is big. As I will discuss in the lecture of tomorrow, when you look at the actual evolution of the quantum modes of the scalar field, the opposite happens. Okay, so that's the non-perturbative effect for the decay of the inflaton. For scalars, it's tricky. For fermions, this picture is perfectly okay. It's just that when the couplings become non-perturbatively large, the kinematic blocking becomes actually more extreme. But for scalars, it turns around and it becomes more efficient. But the idea is the same one. You have kind of a time-dependent Higgs mechanism, and you have to make sure that your process is kinematically allowed. That's all. Okay. So at large couplings, this always appears.
Yeah. Thank you very much. I'm confused. The case of the inflaton field have the negative value. In this case, for example, fermion mass is negative mass, and also the scalar mass squared also the negative. So how can I?
Yeah. That is a very good question. Okay, I like that question. So for the fermions, it doesn't matter. The phase of the mass of the fermion is essentially not important. The only thing that matters is the square. If you go, for example, to the expression of the kinematic blocking parameter, I think there's a typo here. There should be a square. Maybe that's why the things are not so clear. Sorry, there is a typo here. There is a square in this. There should be a square in this bracket. So anything that goes into the computation of the decay rate depends on the square of the mass, not on the mass itself. So for a fermion, the square of the mass is always positive. So there is no problem. There is never an issue there. Same goes for this diagram. But for this diagram, yes, the sign of the mass square of the field can change. And you can get a negative mass in here. So that is a very good question. Perturbatively, the appearance of the negative mass means essentially that in this case, instead of having a blocking, and I forgot, well, I didn't think I would have time to go through that in detail. in this case, this term that goes here could become negative, as you were saying. So minus times minus becomes plus, and this beta, instead of becoming 0, becomes bigger than 1. So you can decay more efficiently into bosons, into scalars, if the mass of the field becomes negative. That's as much as you can do perturbatively, and this plot was supposed to show that if you ignore the effective mass for the decay to a pair of bosons, then you get this dotted line. But if you take into account this mass that changes line, you get this continuous line, and you can see it's bigger. So you get more particle production because the mass became negative. In the perturbative scenario, it's a little bit complicated to understand. Okay, that's just what the computation gives you. When you look at things more in detail, looking at the microphysics in terms of the quantum modes of the field, this is a manifestation of what is called the tachyonic enhancement. It's called tachyonic reheating, essentially. When a field becomes tachyonic, it means that it is sitting at well, I'm sorry, let me rephrase. If the mass of the field becomes negative, that means it is sitting at a local maximum of the potential instead of sitting at a local minimum of the potential. So any little fluctuation that you put on top of that scalar is going to immediately make it roll down the hill to the true minimum of the potential, and that means the fluctuations are growing without control. That's why they're called tachyonic. You're going into you're in the negative mass regime, but that doesn't mean the mass is negative. That only means that the form of the potential of this boson here is becoming of the symmetry breaking type. Okay, so fluctuations can grow a lot, but then the inflaton field becomes positive again, so they have to go back and so on. So they go back and forth, back and forth, back and forth, and that means effectively that you get somewhat of an enhancement in the particle production rate. Hopefully next lecture this will become a little bit more clear. I don't know if you find this a satisfactory solution or not.
Thank you very much for a kind explanation.
Okay, very good.
I think that there are some more questions. I think Shuntaro, maybe you right hand.
Thank you for nice talk. I have a question on the extension of your discussion. You introduced the parameter K for the potential.
Yes.
I think it is the most general. But suppose you have a two-light mode, two-light inflaton, then in that case, I think we have not only oscillation, but you may have a kind of a rotation.
Oh, yes.
I just wonder this kind of extension affect your discussion or not?
Well, that is a very good question, actually. Let me put it this way. As far as I know, as far as I am, I thought I had put the references here. That's a shame. You know, as far as my knowledge goes, this formula, for example, has only been derived for single field inflation models. If you have rotations, I personally don't know exactly what would happen. My guess is that if you have you know, small couplings so that these effects are completely irrelevant, then as always you can use just the vacuum relations to compute the decay rate of one field and the other field separately, let's say. But at larger couplings, yes, the effect of the rotation has to be taken into account. I don't know what the answer is. This is a very good question. Very, very good question. So, you know, what is bailing me out at this moment is the fact that I mentioned that I'm sticking to single field inflation models for now. But your question is very relevant, very good, and I don't have an answer for it.
Okay, thank you.
Next project.
Yes, next project.
Okay, throw him.
Thanks for the nice lecture. So I have a nice question about the kinematic blocking.
Yes.
Is there any observational consequence of the kinematic blocking? Because I suppose that suppression can be adjusted by the adjusting other parameters.
Yes, that is also a very good question. That is a good point because yes, as I was showing in this plot, for example, you see that despite the fact that there is kinematic blocking, at the end of the day, with or without it, the reheating temperature ended up being the same. And if you have kinematic blocking for, let's say, for longer times, you might have a reheating temperature that is lower or higher than you might expect. But as you correctly mentioned, I can just adjust the coupling of the inflaton to the matter to fit the reheating temperature that you get. I think that's what you were trying to say, right? Are there any observable consequences? Observable, I'm not so sure if directly, maybe indirectly. So one reason why, for example, why these sort of dynamics are relevant is on the production of dark relics, for example. If you produce dark matter, the production of dark matter depends a lot on what is the temperature of the universe at a given moment in time. And so some models are more sensitive to higher temperatures, some models are more sensitive to lower temperatures. And as you can see, if you have the same low temperature but different high temperature, then the models for which the sensitivity is up here are going to give two completely different results, despite the fact that you're fixing things down here. The other thing is that, for example, in this case where reheating happens faster, in lecture 3, I'm going to mention a bit the connection between CMB and reheating, to connect the, to determine for how long fluctuations were frozen outside the horizon after inflation, you have to know the duration of reheating precisely. And in that case, if the duration of reheating changes, then, sorry, not just that. You have to know how long reheating lasts, and you also have to know the equation of state parameter for reheating during inflation, okay? For this perturbative case, it doesn't really make much of a difference because at the end of the day, you can readjust parameters in some way. For the next lecture, I'm going to show when this effect is extreme and you actually have non-perturbative particle production, the equation of state parameter can be modified. And so there is definitely a way to parameterize the mapping of modes that you see in the CMB with the inflationary parameters, let's say. But those are kind of indirect proofs of reheating. That is the annoying bit about reheating, that it's not easy. You cannot prove it directly. You cannot see it because it's hiding from us beyond the CMB. So you have to look for indirect clues. So one is dark matter. That's the one that is the most, that allows you to see why this thing is relevant easier. The other one, as I said, are CMB fluctuations, and you can also think of maybe, I'm not sure, that I haven't thought about that. The production of gravitational waves, for example, might change depending on how if you have different reheating stories. But all of those are kind of indirect probes. So directly, yeah, I think it's complicated.
Okay, thank you.
Thank you for your question and discussion. So do you have any more question? Quick one question before we close the session.
Can I ask a simple question?
Yes.
Yeah.
So hi. So when you talk about this kinematic blocking, especially let's say for fermions, the particle production is happening only in like several short periods of time.
Yes.
So is let's say the perturbative picture enough for these scenarios? Let's say, because if it's like a very short period of time, it's usually, like, the adiabaticity of the system is sort of broken and the processes become very non-adiabatic. So is
Exactly.
this like perturbative picture? I don't know if like this perturbative picture will always be like the most efficient way to describe it. So don't
Yeah.
you have to include everything like the
Yeah,
non-perturbative?
let me thanks for the question, because this can be seen as an introduction for tomorrow's lecture. Let me put it this way. So here we are keeping the adiabaticity, let's say, by hand, by writing this decay rate not only as the squared amplitude weight by this kinematic factor, but we're also averaging over oscillation. So in that sense, we're kind of smoothing out the this very short time behavior. But of course, as you say, if you have these sudden crossings of the inflaton that change the mass of the particles so suddenly, then adiabaticity is violated, and you have to do a much more, well, not much more, a slightly more sophisticated analysis. That is what I'm going to talk about tomorrow. In fact, what happens when this is present. In any case, I mean, to me, these perturbative approximation with even taking into account this kinematic suppression is surprisingly accurate for some couplings, okay? Sometimes you would expect non-perturbative effects to become important immediately after, for example, this parameter R becomes bigger than 1. Surprisingly, that doesn't happen. There are regimes where the non-perturbative computation and this computation actually match very well. So there is a what is the word that I'm going to say? There is well, it makes sense to keep this in mind. Let me put it that way. Okay, it's not just a waste of time. It actually helps understand things quite a bit. In fact, if you are familiar with preheating, because maybe that's why you're asking this question, this parameter R here that tells you how big the kinematic blocking is precisely the resonance parameter of non-perturbative particle production. So the two effects are related. There is a range of couplings where this perturbative kinematic blocking and the non-perturbative solution are the same. If you keep increasing the couplings, then yes, it completely fails and you have to do things more carefully. So that's tomorrow. That's the whole point of tomorrow.
One more thing. So when you said like the perturbative picture and the non-perturbative picture is like matches surprisingly for several coupling ranges, is that in coincidence or is there like a physical reason for that?
Well, I think the physical reason is this one. Essentially, there is kind of a threshold of non-adiabaticity that you have to cross, so that there is a splitting between the perturbative and the non-perturbative one. So anything below that threshold, this picture is more than enough. You don't have to do anything else. If you cross that threshold, then yes, let's say exponentially large effects play a role. And of course, you cannot fit anything exponentially with perturbation theory, right? So it's like, instantons in quantum field theory and so on. Like, as long as exponentials are involved, then anything perturbative just fails. So the same thing is true in that case. You can even go to, so naively, for example, you would say, perturbation theory is when the effective coupling is less than 1. That's not the case. You can make it even 1 order of magnitude bigger and it still works surprisingly well. So that's, I mean, quantitatively, yes, it's related with how big the exponential enhancement or blocking is present. And I'm going to show some plots and animations so that we can see it explicitly.
Okay, thank you for your answers. I think that will be the next theme, the theme of the next lectures, the preheating related this parametric resonances. Thank you for your nice lecture to Marcos Garcia and the good presentation, the participation and discussion from the audience. Okay. Thank you. I'll see you and again tomorrow at the same time at the course.
Yes.
Thank you.